So our plan today is to cover some more frames and machines problems. That's our, main thing on our agenda. And I decided right at the beginning to sort of tell you what I'm planning on telling you today. All right, so you see it up there in the green box. You can kind of look at those while you're copying our first problem down, which you see right there. There's a few items that I have on the agenda that I'd like to touch on today. So we are going to pick up a few more types of sort of elements that you might see on the problems that you have to solve. And the first one of those that I'm going to mention here is that you need to be able to know what to do with springs. Okay, and I don't think springs are actually new probably to any of you. I'm sure these are the kinds of things that you've probably seen in a physics class or something along the way. So we're going to touch on that, what to do with a spring. Going to show how once you figure out forces in a frame and machine problem, very often that is information that you can feed on into a next phase of the problem, which might have something to do with stress. And stress in turn would have something to do with knowing how close you might be to breaking something, right? So I'm going to show you how that works for this problem that we have coming up. Distributed loads. This is another concept that I'll introduce the idea of it today. And there will be a later lecture where we go into more detail about what to do with distributed loads, but I'll at least kind of talk through what they are today. I'm going to talk about what the word small means, okay? Because you might sometimes see the word small in various contexts in certain problems, and we can usually do something with that word. Usually that's a clue that allows you to make certain assumptions that makes your problem a little bit easier. I'm going to talk about a couple of different types of connections where you're going to end up with not only force reactions, but moment reactions. Okay, so we'll look at a couple of examples of that. One of the examples I do today I would consider to be a machine as opposed to a truss, not truss, as opposed to a frame. So that'll be kind of interesting, and I'm going to introduce you to another term that is often used called mechanical advantage. All right, so these are what my goals are for the day, and hopefully we make it through all of those. All right, so a lot of you are sitting here trying to frantically take notes and try to figure out, how to get this stuff in your notes. So let me go through some of the first, ideas of this problem that I have shown right here. It says there a force of F is applied to the end of the rope that is tied to the end of the spring. Okay, and after it is tied to the end of the spring, it goes around this frictionless pulley. And it says there that the force of F causes that rope, the end of the rope, to move 15 centimeters in response to that force of F. Okay, that in real life would make all of the members potentially flex some. Like all the members might deform a little bit under a load like that. But to make your life a little bit easier and to make this problem a little bit more solvable for us at this point, I'm going to say let's assume that the bodies that are involved in this problem, namely like member AEB, member DBC, as well as maybe even the small roller and the pulley that's there and everything, we're going to say all of that stuff we're assuming is rigid. Okay? So if I say all of that stuff is rigid, I'm leaving one element out, not saying it's rigid, right? Which one do you think I'm talking about? The spring, I'm going to assume, is not rigid, okay? And the spring will behave according to a spring constant of 10 newtons per millimeter, all right? So what we can do with that is we can take that force that the rope moves, and we'll be able to combine it with that spring constant to figure out how much force might be applied in the rope. Okay? So we'll talk through some of that. What we're supposed to find, okay, here are part A, the shearing stress in the pin that holds the pulley on member CBD. Also, the shearing stress carried in the pin at A, and then also the reactions at C. Okay, so those are the pieces of this problem that we're supposed to find. We may find some other things along the way too, but those are what we are tasked with finding. Okay? All right, so where do you want to start? Okay, someone says a free body diagram, and generally speaking, that is a good answer. We might want to do one thing before we do any free body diagrams for this problem, though. What do you think we might want to think about? Say what? Can we remove any components? Okay, I like that idea. What do you have in mind?
Like the roller or the pulley.
Okay, the pulley in particular is the one that I would look at and say, I might be able to do something else with that pulley. Okay, so I like that idea. Maybe we can simplify this thing down by removing that pulley somehow. Before I do that, though, is there anything I can do to figure out what this unknown force of F is? Okay, what information do I have that I might be able to find F? I have a spring constant and a deformation, and all this extra information I gave about everything being rigid leads to the conclusion that all of that deflection, all of that change in position of 15 centimeters is coming out of the spring elongating. Okay, so what's the equation for spring elongation? Anyone remember it? Okay, F equals K, that's our spring constant, times, some people might use the letter X, or some people might, I'm going to use one that is how much does it change in length. I'll use kind of a delta like we've used before in here. Okay, so for us, we have a K value of 10 newtons per millimeter, right? And a delta value of what? Okay, 15 centimeters. Now, do those units play nicely together as it stands? Okay, what you'll see here is I've got centimeters per millimeter, right? Which those are measuring the same kind of thing, so there might be a conversion I can put in here of what, you think? Okay, how many millimeters in a centimeter? Okay, there's 10 millimeters in a centimeter, because a milli is a thousandth, centi is a hundredth, so there's 10 millimeters in a centimeter. And so I should probably set up something like this where I say 10 millimeters per centimeter, like that. And what does this tell me in terms of what the F is going to be? Looks to me like that should count. 10 times 10 is 100. 100 times 15 is 1,500, right? And that's going to be in what kind of units? Newtons, okay? So very first thing we did here is we figured out that this F is actually going to be equal to 1,500 newtons. Okay, it's a good little warm-up. What we want to do next, we mentioned just a second ago that maybe we want to try to simplify this thing by replacing certain elements with forces, perhaps. Okay, and I think we mentioned that maybe the pulley would be a good candidate to think about replacing, right? Now I've got the word small written there and pointing to that little pulley, right? What do you think the word small means? How should we interpret that? And what should we do if we see that word on a homework problem? You can kind of think of it as having no negligible size, right? What would happen if you took sort of the limit as the size of that pulley went smaller and smaller down to nothing? Okay? What you'd see is that basically that line of E to D is going to basically exist right over the top of the pin, right? And we're given dimensions about where that pin is located. So that's really what the conclusion is going to be, is this. We can get rid of the pulley. Truth is, we can get rid of this force over here as well. And what should we put there instead? Okay. There's the force that was coming here from the rope. That was a 1,500 Newton force like this. What else can we do maybe? right? Let's talk about the spring, right? If you've got an extension spring, extension springs behave like two force members because they are two force members. All they have is a force trying to elongate them on one end and another force trying to elongate on the other end. And so that's basically a member connected at two locations with what amounts to frictionless pins. And so we can treat that spring that we have right here as a two-force member. And one way for us to do that is to just go ahead and put in that we have a force coming up right here and a force coming down, each of which are 1,500 newtons. Okay, so I like that suggestion. We did that before we even really started drawing free body diagrams. We simplified the given information just based on how we know a pulley behaves and how we've seen how a spring behaves, just like a two-force member. Okay, good stuff. So now, you guys said a second ago that we needed to do a free body diagram. Now I think you're right. I think that's what we need to do next. So the question is, which free body diagram should we do? Okay, we could do both of them, but we are always trying to do this in as efficient way as possible. So we should always try to ask the question, is there something we can find quickly? Is there one value we can find quickly? And I think I heard a couple people over here murmuring B, right? If you look at body AEB, what you'll see there is that there will be two things I end up drawing on my free body diagram that are unknowns at A. There will be one thing that's an unknown on the free body diagram that I draw at B. And there's a really nice type of equation we can use, a moment equation, where you pick a point to some moments around, and it can eliminate two forces that have intersecting lines of action, right? So I like the idea of looking at this diagram and immediately sort of seeing that member AEB is a simple enough free body diagram to draw and get something quickly, right? We'll know something more after drawing that free body diagram and doing one equation. It's probably worthwhile doing, okay? So let's go ahead and do that. Okay, so as you've seen me do up here before, I'm going to simplify kind of the shape of this diagram a little bit. It is basically just a straight line. Okay. And what sorts of forces need to act on this straight line from A to B? Okay. So the easy one to kind of look at quickly is the reaction forces at A. We know this because it's a pin, and a pinned connection connected to a rigid support like that has two components of reaction possible that hold it where it needs to be. So I'll call this RAY and this RAX. Okay, another one that's relatively easy is what? E. 1,500 newtons. Okay, so those are the easy ones. I think it's probably a good point in time to talk about this thing that I mentioned, a distributed load. Okay, when you look at things in real life, it is actually pretty rare that you see something that truly is a concentrated load. As a matter of fact, an argument can be made that would say nothing is really a concentrated load, right? Think of this. If I start pushing on something with a true, like, mathematical point, right? Something that really has zero size, right? And you start putting a force between two pieces where the point that I'm trying to push into the other piece literally has zero size. That would be the true definition of a concentrated force, right? Does that make sense? Well, what would that do to stress? right? Stress is force over area. We're saying area, because the size of that thing is going to 0, the area is going to 0, force over 0 area would be infinite stress, right? And materials can't carry infinite stress. Like, there is no material that can carry an infinite stress. So what we always do when we use these concentrated forces on these diagrams, we understand what we mean by them, but technically they're not even possible, right? If you're really, really technical, you would say, I don't really think that's actually possible. Well, a lot of times it doesn't matter. A lot of times the conclusion would be the same. In other words, the force acting on a pin so that that pin causes a kind of a bearing stress on the inner surface, it ends up being the same as if we had a concentrated force. And so we use the term concentrated force, and we use this concept a lot, even though it's not something that actually exists. But we do have some other ways that we can talk about distributing forces. And this is one of the ways that we can denote that is with a little shape like that. And really what that is it's like a graph that says, imagine the height of those little red lines, right? This red line that comes up here and this red line that comes down here. Imagine that height is proportional to some kind of a force per unit of length, right? So that if you could like slice out a tiny little piece, let's say a tiny little length right here, then you would say over that little length I could take my force per length and multiply by that little length, and I could get a reasonable enough idea as to how much force is applied just in that little slice, right? So I mentioned a second ago, we're going to do this in a lot closer detail, but what do you think you might be able to surmise if the shape of this distributed load is symmetric? What would you think? Where would the line of action be for the overall force caused by that 1,500 newtons per meter? Okay, by symmetry, you would think that it's going to have to be somewhere near the middle. And we'll study a little bit more as to why that is, but that is true. If it's a symmetrical shape, then you can assume that the line of action is going to exist at that line of symmetry. Okay, so that's good. We know where it acts. How much acts? Like, what's the total amount of force, would you think? You can take the area of the triangle, the graph triangle, right? And that makes sense because what you're really doing is you're taking almost an integral over this length of the value times, let's say, dx, right? And you take the integral over that whole thing, it's like you're slicing it up into these little pieces, and you end up getting the area of that triangle. So again, we have a whole lecture where one of the things that we talk about is this idea. But for right now, I'll just mention that what you can do is just take the area of that triangle. Okay? So what would the area of the triangle be? Okay? 1/2 base times height, and this is going to end up being a force that acts here in the middle. I'll say 1/2 of the base. The base is going to be 7 meters times the height. The height is 500 newtons per meter. Okay? And you can see there, even the units work out. What do we end up getting there? Oops. There we go. 1750. Okay, 1,750 newtons. All right, so that's, at least a preliminary view into what to do with a distributed load. Okay, we can replace it, as far as this free body diagram is concerned, with an equivalent concentrated load right at the middle, and it's at the middle because the middle contains that line of symmetry. Okay, are we done yet? No, the thing we're actually trying to find is this little guy over here, right? So let me just call that F sub B. Okay, we know that what else do we know about that force? Okay. Yeah, so yeah, what we notice here is that the force is going to be perpendicular to this line, and this line is elevated from horizontal by 40 degrees. Okay? What does that mean in terms of the angle, for the force itself? Okay? The way I think it's easiest to show this is to show that 40 degrees basically right here. Okay. Good stuff. What am I missing on here right now? Okay. I need some lengths. So let me say this. I've got 2 meters to this location, right? You might already have this idea that what I'm going to end up trying to do is summing moments around A. That's what I'm going to shoot toward. So let me actually define some of these other lengths that we might need relative to that same location, right? How far is it from point A to where this concentrated load is being applied? 3.5 meters, I heard someone say, right? 3.5 meters because it's going to be half of the overall length from A to B, which is 7 meters. Okay, and what else? Okay, I'll probably I can either put 5 meters past the 2, or I could just put 7 meters directly right here. And just as a comment before I move on, those of you who get used to doing like mechanical drawings someday, most of you probably don't have a lot of experience with that just yet. This that I've drawn here, that's actually generally a better way to dimension things than the way I do a lot of my figures in this class. To choose one line that's sort of your datum, is what they call it, and then do all of your dimensions relative to that one line. So I'm not going to go off on that too deeply, but I will mention that the way I dimension things in this class is convenient for making figures that are possible, right? It's easier for me to avoid making something impossible accidentally by putting wrong numbers in things, but it's not necessarily the best way to dimension things if what you're trying to do is to tell someone how to build a part. Anyway, that was a little bit of a sidetrack note. What should I do now? Okay, it says some, I actually think some moments, right? Some moments around A. And what components do I have that would cause moments around A? Okay, 1500 would be a negative moment because it's going clockwise, and I've defined counterclockwise to be positive. So that's 1500 newtons times 2, yes. 2 meters. Okay, then what? Minus 1750 newtons times 3.5 meters. Then what? Okay. We also have this force at B that's angled at 40 degrees, which means I don't want the entire force at B. I only want the component that is perpendicular to this member, because that's going to be the component that actually creates the moment, right? The component that goes horizontally will not create a tendency to rotate. So I take FB and multiply it by what? Cosine 40 degrees, and multiply that by 7 meters. Okay? And that's pretty much everything. So I can very quickly get F sub B. Yes, thank you. Someone said, I've got a plus sign that I should have put right here. Okay, FB now is going to be equal to 1500 times 2 plus 1750 times 3.5. Okay, that value divided by the cosine of 40 degrees times 7. 1701.7. This is going to be in newtons. Yes. Okay. Yeah, the question just was, why should it be cosine of 40? And the reason is we're trying to get that adjacent component to where that angle's measured. That makes sense? Okay, so there's a reaction that I have right there, a force between the roller and that other part. And by the way, there's that word small again. Why do you think it's important I say that's a small roller right there? Yeah, it might make a difference in terms of where exactly that force is applied if that roller was really big, right? So I'm just indicating I don't want you to think about the size of that roller being an issue in this problem. Yeah. Okay, the question was, how would the problem change if it was bigger? If it was bigger, the problem wouldn't necessarily change for the roller itself, especially if the dimension was given relative to the center of the roller. It might change for member AEB because the actual location where that force is being applied might shift if that roller was bigger, than almost nothing, right? So anyway, that's why I'm saying it's small. So there's one answer. Were we supposed to find that? No, but it's going to be helpful for us anyway for the things that we are supposed to find. Like what? Okay. Well, one of the things we're supposed to find is the shearing stress in pin A, right? Actually, part A said we're supposed to find the shearing stress in pin D. We didn't need anything. We didn't solve anything to find that, right? I'll come back to it here in a minute and get that shearing stress in pin D. But I'll go ahead and shoot for trying to find the shearing stress in pin A. To do that, what do I need? Right, I need to do sums of forces in the x and y so that I can figure out what RAX and RAY would be, and those can be used to find a total force at A, which then can be used to figure out how much stress happens in that pin. So let's go ahead and get started with that. Summing forces here in the x direction. Okay. I will have RAX minus FB. FB is 1701.7 newtons. But not the entire FB. What do I need? What component do I need? The horizontal component, so I multiply by, here I'm going to do sine of 40 degrees because I need that opposite component to where the angle's measured. Okay. And this will be summing to 0. So RAX ends up being just 1701 times the sine of 40 degrees. 1093.8. Okay, newtons. Right, we do something kind of similar here for the y direction. I'm going to have RAY minus 1500 newtons minus 1750 newtons plus FB, but not the entire FB. I need to take the vertical component, which I get by multiplying by cosine of 40 degrees. Right? All of this should sum to 0. So I'll pull up this again. Here I'll end up with 1500 plus 1750 minus, okay, I put this in as FB, but I'll go ahead and substitute in my 1701.7 here at this point. times the cosine, of 40. And that'll give me 1,946.4. newtons. Okay. This is for RAY. Okay. Mentioned it a second ago, but what are my steps now to find stress? I have two components of force that I've now found at A. I need to find that resultant force acting at A, because that's what we use to figure out how much shearing stress happens in the pin. Got a question? Okay. So to find that resultant force, all we do, I'll call it RA without a subscript. All we do is we take a square root of the sum of the squares of the two components. 1,093.8 newtons squared plus 1,946.4 newtons. Okay, that squared. So RA is just equal to the square root of 1,093.8 squared plus 1,946.4 squared, which gives me 2,232.7. newtons. All right, we're still not at stress. What do I need to do stress? Okay, you might notice right up here at the beginning, I indicated some detailed drawings of the pin at A and another one of the pin at D. Okay, at A, the diameter of the pin appears to be 8 millimeters. And how many shearing planes are there? Just one, okay? And I'm going to go ahead and use this term here and say this example right here is called single shear for a pin. Okay? You might have an inkling as to what we might talk about later, but this is an example of single shear. Okay? It means we just have one shearing plane for that pin. So to figure out the shearing stress that happens in that pin, we'll just take this force, right? The shearing stress is going to be equal to the force of 2,232.7 newtons over what? The area, which is going to be one area of the pin, which would be pi times that 8 millimeters, right? 8 millimeters was the diameter. That squared over 4. Okay? Now let me show you something before I even calculate this. Think of what a Newton per square millimeter is. All right, give myself a little room here. So a Newton per square millimeter. Because that's what this would come out in, right? What if I take that square millimeters, right, and I try to convert it to square meters? What's that conversion? Okay, 1,000 millimeters in a meter. And I have to square that. What is 1,000 squared? Okay, 1,000 squared is 1,000,000, right? So this is saying I have 10 to the 6th newtons per square meter now. What is 10 to the 6th newtons per square meter? Okay? So this is a handy little, it happens to be this way. No one set it up that way on purpose, I don't suppose, but it's a handy thing that if we have newtons and millimeters and we do a stress calculation like that, we often don't have to worry too much about the units, because if we see newtons per square millimeter, we know that is the same thing as a megapascal. Okay? Is that a nice little tip? Okay, so because we have newtons per square millimeter for this problem, let's go ahead and put it in here with that value we just came up with over. Here I've got pi times 8 squared over 4. And what I come up with here is already a number that's in megapascals. Okay, 44.42 MPa. Wonderful. So we just answered part B. We started going a little bit out of order there, didn't we? We just answered part B. Shearing stress in pin A. While we're here, why don't we go ahead and use what we just figured out to find the shearing stress that we would have had in pin D. Okay? How would that work? Okay. So go up here and we'll look at what that pin D, how does it work? First of all, we'll see that the diameter is 6 millimeters. But you'll notice that there are 2 places that that pin has to shear for it to come out of that little slot. And so that's one of the reasons this is referred to a lot of times as double shear. And it means we have to double the amount of cross-sectional area when we do our stress calculation, because there's 2 spots on the pin that have to shear for it to be able to come out. Okay? So basically the same idea here. The reaction at D is going to be equal to the square root. What were the forces at D? 1,500 and 1,500. So we'll do 1,500 newtons squared, and I just have 2 of those, right? So let's get that in here. Square root of 2 times 1,500 squared. 2121.3 newtons. Okay, so stress would be what? The force is 2121.3 newtons. Cross-sectional area is going to be 2 times pi times, it was 6 millimeters, right? Okay, and again, that 2 is in there because there are 2 shear planes. Okay, so let me go ahead and start punching this in. Okay, I'll take, in the numerator, I'll take that previous answer, 2121.3 newtons. Down in the denominator, I'll take 2 times pi times 6 squared over 4. 37.5 units. Okay, again, because it's newtons per square millimeter, and we just showed right here that newtons per square millimeter is the same thing as a megapascal, we'll say this is megapascals. Okay, and let me put some subscripts to make this easier to follow. This is the shearing stress on pin A, and this is the shearing stress on pin D. All right. So now we've done parts A and B. And you might think, now for something completely different. And you might be right. Look at that. All right. So what we're supposed to do next is figure out what are the reactions at the support C. Okay? So before I even, you might say, if I asked what should we do next, what would you probably say? Draw a free body diagram, of course, right? You guys have been trained well. And that is the next thing we will do. But let's look real quick at what that symbol looks like at C. Okay? You might notice there's no sort of dot in the middle of where it goes into the wall right there. Okay? If there's no dot given, it's a pretty strong indicator there's no pin there. Right? There's no pin there, so how would you interpret a symbol like that, would you say? It's going straight in the wall. What sorts of reactions can the wall put on body CBD right there where it goes into the wall? All of them. So I like that answer, right? It's not allowed to move any direction. They call that a fully fixed connection point. So when you say all of them for a 2D problem, what does that mean? Can't translate vertically, it can't translate horizontally, and it can't rotate at that location. All three of those constraints are applied at C. Okay? So I'll just say that now, and I'll show you what it looks like when we get to drawing the free body diagram, okay? So let's draw it. There is basically the shape of that body. Okay? And a couple of those forces are easy for us to remember, right? 1,500 pounds at point D there, and another 1,500 pounds going to the left right here. Excuse me, newtons. Haha. Not the same thing, is it? Okay. What else? Okay, we have that force that we found earlier at B, and if you remember the direction that I showed that on my last free body diagram, it was up and to the left, right? What direction should I show it on this free body diagram? Down and to the right. Oop, that's not where it's applied, sorry. FB. Okay, so there's FB, and how do I know what direction FB acts? Okay, again, it's going to be 40 degrees relative to vertical. Just like the last one was. All right, so those are the easy parts. Now let's look at C. Already, whenever we've looked at pins, we have, in that case, for the case of like the pin at A, it has, it constrains the motion for body AEB, both left and right, as well as up and down. So I have two directions of translation. We have that same thing happen on a fully fixed fixture like this, so we need to put those on there. So I'll say, we might have a reaction like this that I'll call RCY. And maybe another reaction on here that I'll call RCX. But we have more than that because not only is it constrained from translation, it's constrained from rotation. There must be something that constrains it from rotation. And the thing that constrains it from rotation is something that's called a concentrated moment or a couple. Those are two synonymous terms. So you can call it a couple or a concentrated moment. Okay? And what you do is you just put that on here and you say, I'm going to assume that I've got, Okay, a concentrated moment, and maybe I'll just call it M sub c. Do I know what direction that couple is going to act just yet? No, but and yet I drew it on there with a particular arrowhead, right? What did I do? I just assumed a direction that the wall is putting a moment on the end of that body CBD, right? So it's not the moment the body is putting on the wall, it's the moment the wall is putting on the body. And I assumed that that was counterclockwise. I don't know if it is. I'm just assuming that so that I can proceed with my math. Okay? Cool. What do you want to do now? Okay? There's actually no wrong answer here. Any one of them we pick, there's only one thing that we don't know, right? So let me actually start with the one that's most new and interesting first, okay? What if I sum moments at point C? Okay? I'm not quite done with my free body diagram, am I? You guys let me proceed too quickly. What do I need to add? Okay, need to show some lengths. Something like this, maybe. Okay, that looks like that's 4 meters, right? Based on the figure that I have up here. Okay, this right here is going to be 3 meters. Looks like. This right here is going to be 5 meters from where FB is located over to here. Right? And for good measure, no pun intended, we'll put some axes on there as well. Okay, back to our next step. Summing forces around location C. Okay, what are some ones you know how to do very quickly? Okay, so the force at D, right? We can look at the forces at D. We can see that the 1,500 newtons to the left, right, is acting at a distance of 4 meters away from C. Okay, 1,500 newtons times 4 meters. Clockwise or counterclockwise? Clockwise, right? If you're pulling left at a location below, that's going to tend to try to rotate it clockwise. So I'm going to put a minus in for that. Then what? The other 1,500 newton force vertically, what direction does it try to rotate? Also clockwise, so I take minus 1,500 newtons. What length is it acting? Okay. 5 meters plus 3 meters to location C. So that'll be 8 meters. Okay? Then what? FB is going to, looks like it'll try to act in a counterclockwise rotation or rotational direction because FB, I don't take all of it, I just want to take the vertical component because if you look at the horizontal component of that force line of action goes through C. So all I want is the vertical component, okay? And it acts in a counterclockwise way around point C. So FB times the cosine of 40 degrees gives me that vertical component, and we'll multiply this by 3 meters. Okay? Good job. So then someone says, you also have to include the moment acting at C. It's a concentrated moment, so we just add it on M sub C. It does not need any length or anything associated with it because it is already just a concentrated moment. So I'll go ahead and say this now. Anytime you have a concentrated moment on a free body diagram, it doesn't matter where it's acting. on the body, you just go ahead and include it in the sum. Okay? So, you know, this problem didn't have this, but let's just say, you know, maybe the problem was different and I had a concentrated moment acting out here around this point. Okay? This is a what if. You don't have to even draw this if you don't want. But if I put a concentrated moment acting out there, what should I do to my sum? Just add whatever the value is of that concentrated moment. And don't worry about lengths or anything. And just you add that into the sum. Okay? So that means I'm done with my sum of moments around point C, which means I can go ahead and start trying to solve it. Okay? So I'm going to actually move everything but m sub c over to the other side of the equation, which means I'll have a positive 1,500 times 4 plus 1,500 times 8 minus FB. What was FB? Okay, 1701.7 newtons. Times the cosine of 40 degrees times 3. Okay? And that should basically be it. So I end up with here 14,089.3 What are my units? Newton meters. Okay. Let me just make sure I got my signs in here correct. Yep, I wanted to make sure I got my negative sign for that 1701. All right. So that's how much of a moment is reacted at point C. And I know this is maybe a little bit early, but I'm going to go ahead and mention that the next phase of this class that we're going to get into, we're going to start talking about something called flexural stresses. Okay? And just like it might sound, flexural stresses occur instead of taking a member and, say, trying to elongate it or make it go shorter, you take a member and you try to bend it, right? And so I'm going to mention here that the moment we see acting there at the wall, that is something that if we're talking about its effect on member CBD, that is a moment we could think of as a bending moment happening in that body. In other words, that's the moment that's going to try to bend this thing right where it comes out of the wall. So that's a little preview of coming attractions. Okay, or repulsions, right? Revulsions even. All right, so let's get on to the next phase. What is that? We're supposed to find all these reactions. What do we need to do next? Okay, might as well start with X, right? Okay, for X I have minus 1,500 newtons plus the horizontal component of FB. Okay, FB again was 1701 point something, 0.7. That was in newtons. But I don't want all of it. I want just the horizontal component. So I'm going to take this and multiply by the sine of 40 degrees. Okay. Plus RCX. And that's going to be equal to 0. So RCX just ends up being 1,500 minus 1701.7 times the sine of 40. 406.17 Units? Newtons. And then we get to our last one here, sum of forces in the y. And there we've got 1,500 newtons minus 1701.7 newtons times the cosine, 40 degrees, right, plus RCY. All this is equal to 0, so RCY is going to be equal to minus 1,500 plus 1701.7 times the cosine of 40 degrees. So negative 196.42 newtons. Okay, notice this. I'll make this comment too. My concentrated moment, m sub c, did it show up in my translation equations, my x and y sums? Okay? It did not, and it doesn't need to. It's a concentrated moment. We don't need to think about any sort of forces that are implied by that. Okay? Because there are no forces implied by that m sub c. All right. So let's go back up here. Have we solved for everything? I think we just now got the reactions, all three of the reactions at C. Okay. Any questions? Did I go too fast? All right. Did I go too slow? Sometimes? Occasionally? All right. Shall we do another example problem? So all of the other examples I've done so far in here, I would consider them to be frames, right? They're not necessarily built to apply force to something. All of the pieces of them look like they should be called members of the truss, or excuse me, of the frame and everything. So now we're going to do one where I consider this to be more like a machine. Okay? Again, there's no real difference in terms of your process of analyzing them. But this is actually inspired by a real thing called a hold-down toggle, a hold-down toggle clamp. Okay? And if you want to see what that kind of looks like, I have a little picture right here. Right? You can put these in various kinds of manufacturing processes to hold something down. The one I have here is a little bit different than that one because mine has a sleeve kind of slider on it that I'm going to show you. It's a little bit different of how to deal with that. But anyway, same idea as to what it's supposed to be doing. The idea there being that you can pull on the handle, and once you pull the handle a certain distance, it will kind of clamp the part where it needs to be. You can do that with a little clamp kind of thing like this. Okay? So let's see what we're supposed to find. It says, when this mechanism is in the position shown. That is a significant statement because I remember when I first started learning some of these principles, a lot of the problems would come to me in the form of a mechanism like this, and it would ask me a question of how much force is put on the part, and the question didn't make any sense to me if no one told me that all I'm trying to solve for is when the mechanism is in the position that is being shown to me with the dimensions that are on the picture. I'm not trying to solve it for any position. Does that make sense? I'm focusing in on just this position. right? And this is a good starting point, right? Very quickly, you would hope that you would come up with some techniques that maybe you could figure out for any position what force would act in the different pieces. But for now, let's just start with a given position, and we'll figure out how much force is acting in all the pieces for this position. Okay, so that very first sentence there is kind of important and help explain what we're doing, at least at this stage. And it says we're supposed to find how much force link BC is carrying, how much force is ultimately applied to the part by member ACD, what kind of reactions might occur at sleeve A. So that actually should be explained a little bit. The way that that connection is supposed to be interpreted, where A connects to the part it's touching there, right? It's supposed to be interpreted as being almost like a cylindrical sleeve, so that it is free to slide up and down along that sleeve, right? What is it not free to do? Okay, two things. It's not free to move left and right, right? It's going to be constrained from moving left and right. What else can it not do? Rotate. Right? So it basically can move one of the three directions we can imagine a body in 2 dimensions moving. It can do one of those three, but it's not allowed to do the other 2 of those 3. Right? So again, it's allowed to move up and down, but it's not allowed to rotate, and it's not allowed to move left and right. Okay? So it's saying what reactions occur at sleeve A, we'll solve for those. And then lastly, it's asking the question, what is the mechanical advantage achieved by this machine? Without knowing anything about mechanical advantage, what would you think mechanical advantage might refer to? Yeah. Essentially, how much force do we get out of the machine for how much force we have to put into the machine? And that ratio ends up giving us this idea of mechanical advantage. So we'll take a look at that here when we get there. All right, so this is the problem. What would you like to do first? We're not going to cry. Okay? Okay, a suggestion here is to make a free body diagram of lever BE. And I like that idea. Okay? I'm going to slide down a little bit here and try to keep as much as I can in the picture. Okay? So what should I do when I draw this diagram of lever BE? Probably just draw something kind of like this, right? And one of the forces that acts on that lever is relatively easy for me to figure out. What would that be? The 50 pounds up at the top. I'll go ahead and start with that. Okay. And then another location might be relatively easy for us to sort of determine what it might be. What location might that be, I'm thinking? Okay. At E, what is that? It's just a pin, right? So I can imagine there being an X and Y component of reaction. At that location. Okay. REY and REX. Okay, so those are the nice, easy ones. Then what? Okay, so look at location B. There's obviously something else going on at location B. And so the question that we have to ask ourselves, because remember, one of our things we're supposed to do is figure out which of our bodies on the diagram have more than 2 forces on them, and which ones are 2 force members. Okay, so does our diagram here have any 2 force members? Yeah, BC is a 2 force member. Look at it. It's connected at exactly 2 locations with frictionless pins. with no external forces applied anywhere else, right? Besides, really none at all, but no external forces applied certainly, anywhere else besides pins. So that is a two-force member. Once you figure out it's a two-force member, why is that important? Why do we need to know that? It means that any force caused by that member is going to be applied along a line of action that extends from pin to pin. So what that practically means is that I already know the direction of force that's applied at B, right? I just don't know the magnitude yet. I can figure out the direction based on the geometry of the problem. So let me put that on there and say I've got this force that acts here at B. What direction do you want to show it? Okay. Yeah, we do need to put the slope on there. I may as well go ahead and do that. How do I know the slope? Okay. I know that it goes half an inch from C to B horizontally, so I can put half right here. What else do I know? 3/4 of an inch vertically from C to B. Okay. But what about the direction of my arrowhead? I haven't even put one on there yet. Okay. So we could show it to where we assume tension. That's the way we've done everything else. You want to do that? Okay. Those of you who are kind of intuitive about this stuff might say, yeah, but I don't think it's going to actually carry tension. All right. Doesn't matter to me. We can put whatever direction you want as far as the direction of the arrowhead. Our solution will tell us whether or not we're right. Okay? So what do we want to name this force? Since we assume tension, let's use the letter T. TBC. Okay, what else should I put on this diagram? Okay, some dimensions. So, if I want, I can show one dimension up to where this force is being applied. How far is that? 2.25 inches, because it's going to be 1.5 inches plus 0.75 inches, and then another 2 inches above that. Up to where the 50 pounds is being applied. Okay. Any other dimensions I need on here? Okay. A distance between B and E. All right. Let me ask this. Do I know enough about this problem at this point? Okay. It's a little bit tricky here. Okay. Which some of the problems you get will be a little bit tricky. Okay. But look at this right here. It's significant that there's this dotted line that goes up to point C, right? It's telling me that it's 1 inch, or really what it's telling me is that E, right, is directly below C. Well, if E is directly below C, then I know that B is 1/2 inch to the left of E, right? I also know that B is 2.25 inches above E, right? So I do actually know both of those dimensions. And what it tells me here is that this dimension right here should be, maybe I'll draw it like this. This dimension, that's a hard dimension to draw on here, isn't it? Maybe I won't draw it right there. I'll draw it over here. Okay. This dimension right here is going to be 1/2 inch. Okay. So then I heard a suggestion just now, could we sum moments around E? It's exactly what I want to do. when I sum moments around E here, I will have a clockwise 50 pounds, so minus 50 pounds, times what length? 4.25 inches. Then what? Minus TBC, because I'm going to take, I have to split TBC into two components here. I'm going to do the horizontal component first. To get the horizontal component, I'm going to take 0.5 over the square root of 0.5 squared plus 0.75 squared. What do I need to multiply that by to make it a moment? Okay, 2.25 inches. Okay, and I have one more component that I need to put in here, and what is that? The vertical component of TBC, which is going to be acting counterclockwise around E, right? So I need to add TBC. To get the vertical component, I'll do 0.75 over the square root of 0.5 squared plus 0.75 squared. Okay, and multiply that by what? 0.5 inch, because that's how far it is from the line of action of the vertical component of TBC to point E. Okay? And I think that's all I've got that would create moments around E. So let me punch all this stuff in and try to solve. Okay, this one, rather than try to factor things out and figure all that stuff out, I'm just going to punch the equation in just like it sits there. So minus 50 times 4.25 minus x, rather than TBC, times 0.5 times 2.25 divided by the square root of 0.5 squared plus 0.75 squared. Okay, plus x, it's the variable I'm trying to solve for, times 0.75 times 0.5 divided by the square root of 0.5 squared plus 0.75 squared. Okay, plug in my equal sign there, and then hit 0, shift, solve. Okay, I don't need to put anything in special for my initial guess, so I'll just hit equals, and it tells me it ends up being negative 255.39. Units? Pounds. The negative sign means what? We assumed tension for link BC. That is not what it has in it. It has a compressive force in BC, and that force is going to be 255.39 pounds. Okay? Very nice. Do I need to do anything more with this free body diagram? Okay. Now, if the question had, for whatever reason, asked you for reactions at E, then the answer would be yes. I would need to do more with this free body diagram. Does the question ask you for that? Okay. It does not, and so in the spirit of efficiency, I'm just going to leave it off. Right? Say I don't need to find those reactions at E. I know how to do them if I need them. Right? What would you do? Some forces in the x to find REX, some forces in the y to find REY. I know what to do if I need them, but it turns out this problem doesn't require that. Okay? So I will go ahead and move on to the next piece, because now I've found the amount of force in the link. So how much force is applied to the part by member ACD, and what reactions occur at sleeve A? So what does it look like we need to do now? Do a free body diagram of ACD, right? And again, I'm going to simplify it. There's ACD, okay? And we just found one of the forces that's being applied to ACD. Now, actually, let's go back and remember the direction that we assumed it went, right? Up there where it connects at B, we assumed it was in tension, right? It was pointing toward C. So when I draw the location at C, what direction should I draw it? Equal in magnitude, opposite direction. So I should draw it pointing up toward B to be consistent. But then if I label it with a value, what would I label it with? Negative, just like I found, 255 point, what was it? 39 pounds. Okay? And I know the slope of that, so I may as well put it in right now. Okay, so I've got 0.5 down here, and I've got 0.75 up here. Okay, what other forces act on part ACD? Okay, remember at A, it is allowed to move up and down. Because it's allowed to move up and down, it means there's no force that's restricting its motion up and down. Okay, and this is assuming that this is a frictionless slider. Okay, so we'll make that assumption. It's a frictionless slider at A. So we're saying it's not restricted from moving up and down, but it is restricted from moving left and right. So I'll call this maybe RAX. And what else? It's also being restricted from rotating at A. So I'm going to put a concentrated moment at that location called MA, right? To say that it's not allowed to rotate at that point. What other forces act on part ACD? Okay. So it looks to me like the part is going to be experiencing this compressive force. So I'm going to show that compressive force that acts on the part, and that effect that happens on this member right here would act upward, right? So I'm going to maybe call this RDY. All right. Am I missing anything? Okay, his question is, are we assuming the part acts like a roller so it can't have a Y component? Right, an X component, yeah. So the answer to that is, it looks reasonable to think of it that way, right? It's got a round shape to it. Looks like it's reasonable that it might not roll. That's a question that's going to be based on the context, right? That assumption would go away if I came in here and said, as we use this machinery, something is trying to push on this part to the right. If I came in and gave you that information, what would you then think might happen at D? Okay? It might have another force that we have to think about in terms of acting on joint D. But if I didn't tell you that, that's not something you should just randomly assume for the purpose of solving these homework problems and that kind of stuff. You shouldn't just say, well, there could be another force acting there, and I'll make up a number and I'll start putting it in there. How did I not get the answer that was on the answer key? I don't know, right? Anyway, sometimes things like that are really good ideas to think through if you're dealing with a real-world problem, and they're not so good ideas to think through if you're trying to do a problem that is you're trying to reach a particular answer in the back of a book or something. Does that make sense? So we're going to just keep it with RDY, but I will acknowledge that having another force is possible if you had different conditions than this. Okay, what else do I need on my free body diagram? Okay, 1 inch and 1 inch. Okay, cool. We're supposed to find how much force is applied to the part by member ACD. What's our equation we should maybe look at first? Okay, summing forces in the y direction looks like a good idea to me. Okay, and I will have an upward force, so positive, but then a negative value of negative or of 255.39. If that makes sense. Upward arrow, so positive, but negative value, so negative. Okay. But not that entire force. What do I need to get to put in my y sum? Okay. So after we figure out that force, the vertical component of force in link BC, what other forces do I have in the vertical direction? RDY. Anything else? Well, that's it. So RDY is just going to be equal to positive 255, which I've actually got that stored in X. I won't even mess with it. 255.39 times 0.75 divided by the square root of 0.5 squared plus 0.75 squared. Okay, that gives me 212.5 pounds. All right. So my reactions at pin or at sleeve A, right? I just finished this one. This how much force is applied to the part by member ACD. So we just figured that one out. Another easy one to do here is to sum forces in the X. Right? And so there I've got the arrow points generally left for 255.39, so I'll put in a minus. But then the value is minus 255.39 pounds. But I don't want that entire value. I want just the X component. Okay, so I multiply by 0.5 over the square root of 0.5 squared plus 0.75 squared. Okay, and that's how I deal with the force at C. Then what? Plus RAX and set it equal to 0. So that tells me that RAX is just going to be equal to what? Positive or negative, you think? Okay. Well, I think of this as I'm going to move this whole term to the other side of the equation, and when I do, one of those equal signs is going to go, or one of those, negative signs is going to go away. Leaves me with just one negative sign. So it'll be negative 255.39 times 0.5 divided by the square root of 0.5 squared plus 0.75 squared. Okay, so negative 141.75 141.66. What was it again? 141.66 pounds. And the negative sign means what? Okay. When I assumed that rod that this part ACD slides on, when I assumed that the rod put a rightward force on part ACD, that was incorrect. It actually pulls to the left on ACD. Okay. So we're almost there. I have one more reaction to find at A. How do I find that? Okay, I'm going to sum moments, and you can do it, about any point you want, but, Okay. Someone said we could sum moments around point A. Want me to do something that might blow your mind a little bit? Yeah, someone says, what if we sum moments around point B? Or excuse me, C. Yeah, that's right. That's point C. Okay. Why might that be a nicer thing to do? Yeah, it gets rid of one more of my forces, and it makes my sum more compact. So I'm going to do that, right? Summing moments around point C. Okay. What I've got for that is RDY, which is 212.5 pounds. Okay. Clockwise tendency to rotate at a length of 1 inch. RAX and the tension in link BC, neither of those forces will create moments around point C. And what do you do with MA? You just add it in.
So you can translate the moment anywhere along that line?
Yeah, when you sum moments and you have a concentrated moment, it doesn't matter where that concentrated moment is, right? It does not have to be at the location you're summing moments around. It can be anywhere on the body, and you still just include it in the sum. So that's what we did here. It's over there at location A, but we don't care. We still just throw it in the sum.
That's why it's a concentrated.
It's a concentrated moment. Yep.
So that would only apply if we're talking about the specific body that has concentrated moment. Is that right? Or would it apply to the whole thing?
That feature that I was just talking about, that if you have a concentrated moment and you're summing moments, you just put that concentrated moment in the sum. You can't do that with forces, because forces, you actually have to think about the length that's associated with that force relative to the point you're summing moments around, right? But with concentrated moments, it doesn't really matter where they are. You just include them in the sum. Yep, it's already a moment. Okay, so this becomes really easy, right? What is this? MA is negative 212.5 inch-pounds. And the negative means I assumed counterclockwise. I assumed that the rod that part ACD slides on was putting a counterclockwise moment on that part, and I assumed wrong. So the rod that it slides on is actually putting a clockwise moment on part ACD. Okay? Clear as mud? All right. Are there any other questions? Oh, thank you. I have one more question to answer, don't I?
Yes.
What is mechanical advantage? I thought I was done. I was trying to escape. Okay, so let's come up with this mechanical advantage. Okay, mechanical advantage is defined as basically how much force you get out. I'll say output force divided by input force. Okay? How much output force do we get for this machine? 212.5. And I had to put in, right, up here on the handle, I had to put in 50 pounds to get that 112.5 pounds. So my mechanical advantage is going to be equal to 212.5 divided by 50. And that would just be 4.25. Any? Okay. Question was, are there any units for mechanical advantage? No, it's just a ratio. So it is a unitless quantity. Yeah, the question is, how did I know what my output force was? Did I choose RDY as my output force just because of the context of the problem? And the answer is basically yes, right? I know enough about what this thing is supposed to be doing that is almost intuitively what the output force must be, because it's where this force is, the effect is felt at that location, right? So yeah, that's fair enough to say it that way.